are going to discuss about a type of extrinsic semiconductor called p-type semiconductor. In the last video, we have seen what are intrinsic semiconductors and n-type semiconductors. So in this video, we can see what are p-type semiconductors. A p-type semiconductor is obtained by adding a trivalent impurity like boron, aluminium, indium to germanium or silicon crystal. If a trivalent impurity means outermost 3 electrons are there. Okay, so such atoms are added to germanium or silicon crystal lattice, we will get a p-type semiconductor. Now, +3 represents the trivalent impurity. When this is added to the silicon or germanium crystal lattice, what happens? It has 3 electrons in the outermost shell. So these 3 represent the 3 electrons of the trivalent impurity. So 3 electrons form 3 covalent bond with the neighboring silicon atom, neighboring 3 silicon atom. Okay, so this electron, it forms bond with here this electron of the silicon atom, here this form covalent bond with this electron of the silicon atom, here also a covalent bond is formed. But here the fourth silicon atom gives an electron, but here there is no electron to give, there is a vacancy of electron. So in this bond there produces a vacancy of electron, because this trivalent impurity consists only 3 electrons in the outermost shell. So 3 electrons form covalent bond with the 3 neighboring silicon atom, but here there is a vacancy formed. So a bond between the fourth neighbor and the trivalent atom has a vacancy, okay, or hole. So here in this bond there is a vacancy or hole. So even at 0 Kelvin or even at absolute 0, there is a hole for conduction. Okay, so there is a hole given by the trivalent impurity for conduction. So this is the hole given by the trivalent impurity. Thus the 3 electrons of the trivalent impurity form covalent bonds with 3 electrons of the neighboring 3 silicon atom or semiconductor atom, but does not have an electron to offer to the fourth silicon atom, isn't it? So the bond between the fourth semiconductor atom and the impurity has a vacancy or hole. Thus hole is available for conduction even at 0 Kelvin. The trivalent impurity gives a hole for conduction, isn't it? Even at 0 Kelvin, this trivalent impurity gives a hole for conduction. We know that hole is positive charge, it can accept an electron. Hole can accept an electron, and hence the trivalent impurity is called acceptor impurity. We know in n-type semiconductor, the pentavalent impurities are called donor impurity. Similarly, in p-type semiconductor, the trivalent impurity is called acceptor impurity. Now what happens if temperature increases? As temperature increases, we know that these bonded electrons get free. For example, this bond break and 1 electron get free. Okay, so as temperature increases, more bonded electrons get free, and they are also available for conduction. Clear? So as temperature increases, for example, this bond break and 1 electron get free means how many electrons are there for conduction? 1 electron is there for conduction. How many holes are there? 2 holes are there, no? So along with the hole given by the acceptor impurity as well as the hole produced by the thermal generation, isn't it? So as temperature increases, for example, if this electron get free means that is a thermally generated electron, and if that electron gets free, what is produced there? A hole is produced there. So 2 holes will be there. 1 hole is given by the impurity and 1 hole is by thermal generation. Clear, children? So as temperature increases, more bonded electrons get free and they are also available for conduction. Thus in p-type semiconductor, holes are generated by impurity and also by thermal generation. Holes are given by the impurity and holes are also produced by thermal generation. But what about electrons? Electrons are produced only by thermal generation. When the temperature increases only, the electrons get free. So electrons are produced only by thermal generation, but holes are produced by thermal generation as well as given by the impurity. And hence number of holes very much greater than number of electrons. Because of this reason, number of holes greater than number of electrons. Similarly, hole current greater than electronic current. Clear? And since the number of holes are greater, holes are called majority charge carriers. and electrons are called minority charge carriers. Maximum amount of current is produced by holes, and hence holes are the majority carriers and electrons are called minority charge carriers. Now we can discuss the energy band diagram of p-type semiconductors. Okay, so energy band diagram, we know it consists of valence band and conduction band. Here valence band and conduction band, and this is the energy band diagram when T is equal to 0 Kelvin. Okay, when temperature T is equal to 0 Kelvin, here for temperature much greater than 0 Kelvin. First we can draw the energy band diagram for 0 Kelvin. Even at 0 Kelvin, there are some holes, okay, given by which impurity? The acceptor impurity, isn't it? Even at 0 Kelvin, there are holes given by the acceptor impurity. So here we can draw some holes, 2 holes. Okay, so these are the valence electrons, and there are 2 holes. For example, there are 2 holes given by the acceptor impurity. No electrons are there for conduction, no? So conduction band is completely empty. Okay, so even at 0 Kelvin, there are some holes for conduction. Holes are given by which impurity? The acceptor impurity. Clear? Now, as temperature increases, what happens? The covalent bond break and some electrons get free, isn't it? As temperature increases, for example, some covalent bond break and some electrons get free, and we can assume that let these 4 electrons get free. Let these 4 electrons get free, and in that position what are formed? Holes are formed, in addition to the 2 holes given by the acceptor impurity. Clear? At high temperature, covalent bond breaks and some electrons get free. Let 4 electrons get free and they reaches the conduction band. And in that position what are formed? Holes are formed, isn't it? So number of holes greater than number of conduction electrons. Clear? So here we can say that 2 holes are given by the impurity and 4 holes are given by thermal generation. So number of holes much greater than number of electrons for conduction. Clear? Now, in an p-type semiconductor, in addition to valence band and conduction band, there is one more energy level close to the valence band. Here we can draw another energy level. Here also we can draw an additional energy level close to the valence band, and that energy level is called the acceptor energy level, EA, that is the acceptor energy level. So in addition to valence band and conduction band, in a p-type semiconductor there is another energy level called acceptor energy level. Clear? Acceptor energy level. And the value of acceptor energy level is, here this value is between 0.01 to 0.05 electron volt. Okay, so this value is 0.01 to 0.05 electron volt. Okay, so as n-type semiconductor, here also what happens to energy level as doping, by doping what happens to energy level? Energy level decreases. Clear, children? So this represents the energy band diagram of p-type semiconductor at temperature equal to 0 Kelvin and temperature greater than 0 Kelvin. We know that for an intrinsic semiconductor, number of electrons and holes are equal, isn't it? For intrinsic, Ne equal to NH is equal to Ni, where Ne represents the number of electrons, NH is the number of holes, and Ni is the intrinsic carrier concentration. Similarly, the electron and hole concentration in an extrinsic semiconductor in thermal equilibrium is given by the formula Ne, that is number of electrons, into NH, number of holes, is equal to Ni square. Ne into NH is equal to Ni square, where Ne is the number of electrons, NH is the number of holes, and Ni is the intrinsic carrier concentration. So for extrinsic semiconductor, for p-type or n-type, The relation between number of electron, number of holes is NE/NH is equal to Ni square, where Ni is the intrinsic carrier concentration. We know that for an N-type semiconductor, Ne is greater than NH. For a P-type semiconductor, NH is greater than Ne, and the relation for any type of extrinsic semiconductor is Ne/NH is equal to Ni square. Okay? Numerical. Pure silicon at 300 Kelvin has equal electron and hole concentration of 1.5 into 10 raised to 16 per meter cube. Doping by indium increases NH to 4.5 into 10 raised to 22 per meter cube. Calculate Ne in doped silicon and identify the new semiconductor. Okay, so here a pure silicon has equal electron and hole concentration. Pure silicon means that represents the intrinsic carrier concentration, isn't it? Pure silicon means that may be an intrinsic semiconductor. For an intrinsic semiconductor, number of electron is equal to number of hole equal to Ni. What is Ni given? 1.5 into 10 raised to 16 per meter cube. Okay, now it is doped by indium. When a semiconductor is doped by indium, indium is a trivalent impurity. What is a new semiconductor obtained? It is always a p-type semiconductor, isn't it? It's a p-type semiconductor. So it is doped with indium. What happens to number of holes? Number of holes becomes, what is its value? 4.5 into 10 raised to 22 per meter cube. Doping with indium, it becomes an extrinsic semiconductor. We know the relation between number of electrons, number of holes and intrinsic carrier concentration is, what is the formula for extrinsic? Ne/NH is equal to Ni square. This is the general formula. So we can write, we have the general formula Ne/NH is equal to Ni square. Okay. So Ne we have to find out, Ne equal to Ni square divided by NH. There we can substitute 1.5 into 10 raised to 16 divided by NH, 4.16 the whole square, divided by 4.5 into 10 raised to 22, and after simplification you will get the answer as 0.5 into 10 raised to 10 per meter cube. Okay, 0.5 into 10 raised to 10 meter cube. So number of holes 4.5 into 10 raised to 22 per meter cube, and number of electron is 0.5 into 10 raised to 10 per meter cube. So number of holes greater, no? So what, how will you confirm it is a p-type semiconductor? Since number of holes greater than number of electron, it is a p-type semiconductor. Otherwise we can say, since it is doped with indium, and indium is a trivalent impurity, that also we can say that it is a p-type semiconductor. Clear, children? Question. A semiconductor has equal electron and hole concentration of 2 into 10 raised to 8 per meter cube. On doping with certain impurity, the hole concentration increases to 4 into 10 raised to 10 per meter cube. What type of semiconductor is obtained on doping? Calculate the new electron concentration. How does the energy gap vary with doping? Okay, so a semiconductor has equal electron and hole concentration. So what is given here? A semiconductor has equal electron and hole concentration means that represents the intrinsic concentration, isn't it? So intrinsic concentration is 2 into 10 raised to 8 per meter cube. For an intrinsic semiconductor, number of electrons and holes are equal, isn't it? So Ni equal to given. On doping with certain impurity, hole concentration increases to 4 into 10. So what is the hole concentration? NH equal to 4 into 10 raised to 10 per meter cube. Okay, and we have to find out the electron concentration. So Ne equal to question mark. So we have the relation Ne into NH is equal to Ni square. Clear? So Ne is equal to, we can substitute, Ni is 2 into 10 raised to 8 the whole square divided by 4 into 10 raised to 10. So on simplification, its answer is 10 raised to 6 per meter cube. So electron concentration is equal to 10 raised to 6 per meter cube. So here number of holes greater, no, than number of electrons. So number of holes greater, and therefore what type of semiconductor is obtained? So semiconductor is what type of semiconductor? Since number of holes greater semiconductor is a p-type semiconductor. Clear? So since number of holes greater than number of electrons, the obtained semiconductor is a p-type semiconductor. Now, how does the energy gap vary with doping? We know that on doping, an additional energy level is produced, isn't it? In n-type semiconductor or p-type semiconductor, in addition to valence band and conduction band, there is another energy level developed. What is that energy level? In p-type semiconductor, it is called acceptor energy level. In n-type semiconductor, that energy level is called donor energy level. So, what happens to forbidden energy gap? Forbidden energy gap decreases, right? Forbidden energy gap decreases on doping. So, forbidden energy gap decreases on doping. Clear, children? Give the ratio of number of holes and number of conduction electrons in an intrinsic semiconductor. Second part, what happens to the energy gap of a semiconductor when temperature is increased? So, what is the ratio of number of electrons and number of conduction electrons in an intrinsic semiconductor? We know that for an intrinsic semiconductor, number of electrons and number of holes are equal, isn't it? For intrinsic, number of electrons and number of holes are equal. So, what is the ratio? So, ratio is Ne divided by Nh is equal to, what is the ratio? 1:1, isn't it? Now, what happens to the energy gap of a semiconductor when temperature is increased? When temperature is increased, what happens to energy gap? Energy gap remains same. There is no change, because as temperature increases, the valence electrons get enough energy to move to the conduction band. Okay, but the forbidden energy gap remains same. There is no change in the forbidden energy gap. So, when electrons move from valence band to conduction band, when temperature increases, the electrons, valence electron get enough energy to reach the conduction band by overcoming the forbidden energy gap. So, there is no change in the forbidden energy gap on increasing the temperature. On changing temperature, so on increasing the temperature, no change in energy gap. Okay, but on doping, what happens to forbidden energy gap? As discussed in the last question, on doping, forbidden energy gap decreases, but as temperature increases, there is no change in the energy gap. Suppose a pure silicon has 5 × 10⁻28 atoms per meter cube. It is doped by 1 ppm concentration of pentavalent arsenic. Calculate the number of electrons and holes. Given Ni equal to 1.5 × 10⁻16 per meter cube. So, here what are given? Ni, intrinsic carrier concentration, is 1.5 × 10⁻16 per meter cube. This pure semiconductor is doped by 1 ppm. ppm means parts per million concentration of pentavalent arsenic. Okay, so it is doped with pentavalent arsenic means which number is greater? Number of electrons will be greater, no? So, this represents the number of electrons when a pure semiconductor is doped with a pentavalent impurity. So, when it is doped with a pentavalent impurity, number of electron increases, no? So, Ne equal to 5 × 10⁻28 atoms per meter cube, but it is doped with 1 parts per million. Parts per million means this one divided by million. Million means 10⁻6, isn't it? Parts per million. So, 5 × 10⁻28 per million means divided by 10⁻6. So, per million means divided by 10⁻6. So, that is 5 × 10⁻22 per meter cube. Okay, this is number of electrons. Why it is taken as number of electrons? Because it is doped with a pentavalent impurity. Now, we have to find out number of holes. Number of holes equal to question mark. Again, we have the general formula NeNH is equal to Ni square. Okay, or NH is equal to Ni 1.5 × 10⁻16 the whole square divided by 5 × 10⁻22. On simplification, you will get 4.5 × 10⁻9 per meter cube. So, this represents the number of holes and this is the number of electrons. Number of electron is greater than number of holes. Therefore, the obtained semiconductor is a n-type semiconductor. Okay.